This lecture is going to be on amplitude and wavelength, and here's the symbol for wavelength of lambda. Amplitude describes the net displacement that an oscillator is from zero or equilibrium. When we graphed the pendulum that it was oscillating, we said that the amplitude is going to be the difference between the highest point and equilibrium. So here I have an amplitude, and here I have an amplitude. The wavelength, lambda, which is signified by this symbol right here, is the length from crest to crest or trough to trough. In other words, from crest to crest or trough to trough. Or any location within the graph to another location at the same position in its cycle. In other words, we could say from this location from equilibrium to this location equilibrium, where it's gone through one full cycle. So we're looking at a couple terms here, amplitude and wavelength. And you can watch this video. You can go back and watch this. This is actually on the PowerPoint. This is on the website. So here we'll look at period and frequency. Period is the time for a particle on a medium to make one complete vibrational cycle. Period, being a time, is a measure in units of time such as seconds, hours, days, or even years. The period of orbit for the Earth is 365 days, the time it takes to complete one cycle. Frequency describes the number of waves that pass through a place in a given amount of time. Frequency and period are distinctly different, yet related quantities. Frequency refers to how often something happens. Period refers to the time it takes something to happen. So here we can see the math here. The period, written by the letter T, equals 1 divided by frequency. Notice frequency is measured in hertz. Period is measured, in this case, in seconds. These are inversely related. Period and frequency have inverse relationships. The greater the T, or the period, the lower the frequency. So here I can see frequency is equal to 1 over T. So frequency measured in hertz is 1 over the period in seconds. So here we're going to solve for period and frequency. So here we go. Solve. What is the period of an oscillator that takes 8 seconds to complete 4 cycles? What is its frequency? Well, let's see. So period and frequency. Period is going to be 2 seconds. If it takes 8 seconds to go through 4 times, 8 divided by 4 is going to be 2 seconds. The frequency is going to be 1 divided by 2 seconds, so 0.5 hertz. So solve this one. If it takes 1 hour for a person on a swing to oscillate 3,000 times, what is the period of the oscillator? What is its frequency? Well, you would find that if it oscillates 3,000 times, in 1 hour, there are 3,600 seconds. I know that there are 60 minutes in an hour, and there are 60 seconds in a minute. So 60 times 60 is 3,600 divided by 3,000. The period of the oscillator is 1.2 seconds. That's how the time it takes to go through one cycle. The frequency would be 1 divided by 1.2, or 1 divided by the period of 1.2 seconds, which is 0.83 hertz. So here we're going to solve a problem. We're going to use the picture here. Notice I have different locations on this little graph here. We're going to make sense of it. So how many wavelengths are shown in the picture? How many times did the oscillator move back and forth? How many crests are in the picture? How many troughs? It's having you look at what we have going on in this picture here. So how many wavelengths? Well, I know from A to E is 1 full wavelength, and from E to G is a half. So there's 1.5 total wavelengths. How many times did the oscillator move back and forth? Well, if it moved back and forth 1.5 times, right? If the wavelength is 1.5 wavelengths, it's got 1.5 oscillations in this picture. So how many crests? 1 at letter B and 2 at letter F. How many troughs are in the picture? Just letter D here. So what do the letter combinations below show? So for example, A through E shows 1 full wavelength. So A, B, C, D, and E is 1 full wavelength. So A to C would be a half a wavelength. B to D would be a half of a wavelength. E to F would be 1/4 of a wavelength, and D to G would be 3/4 of a wavelength. If the length of letters A through G, right, A through G, is 6 meters, what is the size of one wavelength? Well, because it's 1.5 total wavelengths, you would find that each one of these segments is going to be 2 meters. So 2 meters for half, 2 meters for half, and 2 meters for half. So that means half of it's 2, other half is 2, so 1 full wavelength is 4 meters. If the time in the graph is 3 seconds, what is the period of the pendulum? Well, that means if the total time from A to G is 3 seconds, that means this segment is 1 second, This segment is 2 seconds, and this segment is the third second. So that means it takes 2 seconds to travel from A to E. So in this case, what is the frequency? Well, we're going back to using, if we know the period is 2 seconds, 1 over 2 is 0.5 hertz. So what is the wave speed? If it traveled 4 meters in 2 seconds, the wave speed is going to be speed equals distance divided by time. We would find that the wave speed is 2 meters per second. So here's the answer key. And you can check this, and you can go through this on your own and make sure you check to make sure you know how to solve this. So here's another problem you can work from. Solve using the picture. Provided information. The graph comes from a pendulum that oscillated 3 oscillations back and forth. Right? Here's 1, A to E. Here's 2. Here's 3. The length of the graph along the x-axis from A to G is 18 meters. The amplitude is 2 meters. It took 9 seconds to oscillate 3 times back and forth, and we will assume there's no friction, so no damping took place. So what you're going to do is you can answer this. The answer key is on the next slide. I want you to make sure you go through here kind of slowly. I'm not going to go through each one of these. I'm going to let you take a look at the answer key. The size of one wavelength here, we would see, is 6 meters. If it's 18 total, one full wavelength would be 6 meters. And I trust that you'll be able to use the answer key to solve these problems for yourself. Good luck.